Okay, good morning. We will start a little early today. So we are winding up determinants. So let me. So this is the topic that we were looking at for the last few classes. So for every n bigger than or equal to 1, we defined a function from the space of n cross n matrices to the corresponding field. Since we are mostly looking at real matrices, the determinant will have real values. So often we drop the subscript n, just call this dit, and we proved that the determinant has a number of properties. Most importantly, one, it is multiplicative. If I take two square matrices of the same size and multiply them, the determinants multiply. Two, det A is non-zero if and only if A is invertible. And three, let me just check. Yeah, the determinant of the identity matrix is 1. So these are the most important properties of the determinant. So we proved all this by somewhat circuitous way. You know, it was not by just taking an expression for the determinant and just a brute force computation. There was a strategy to the way that we approach these results, and the strategy is exactly the strategy that I stole from Artin. So the lesson is that often you do need a strategy to uncover deeper aspects of mathematics. So you should keep this in mind. So then, having finished the topic of determinants of square matrices, we began. Is there a question? No. Just 1 second. A closely related topic. So determinant of linear maps V to V, dim V, finite. So recall that M n cross n R is the same as linear maps M n cross 1 to M n cross 1. So you can really think of what happened before as in this context, that in the specific case when V is the space of column matrices of length n, column vectors of length n, we are giving a map from the space of linear maps from this vector space to itself to the real numbers, and it has all these properties. Okay, so I'm going to define the determinant of a linear map, but as a preparation, note that if A is a n cross n matrix and T is an invertible matrix, then dit of A is equal to dit of T A T inverse, because this proof is trivial. Proof is trivial. RHS equals dit T dit A dit T inverse, and dit T and dit T inverse, this is dit T into dit T inverse into dit A, because the real numbers are commutative and the product of real numbers is commutative, and this is dit of I, which is 1. So we get equal to dit A. Okay. So if I have A and I transform A according to this, so restatement of above. If A and B are square matrices of the same size, we say that A and B are similar if there exists invertible T such that A equal to TB, B equal to TA, T inverse. So the restatement similar matrices have equal determinants. So if you are familiar with equivalence relations, by now you should be, but so let me just take a poll. I mean, informal. Let me just ask you, have all of you encountered equivalence relations on a set?
Yes, sir. I think it was part of the standard 12th grade syllabus for, I think, every board. I'm not sure about everything, but at least we had, yeah.
Okay, so you know the notion of an equivalence relation, everybody. Yeah. So what? So summarize. So similarity is an equivalence relation on the set of n cross n matrices, and dit A is constant on the equivalence classes. So whenever I have an equivalence relation on a set, that set gets partitioned into equivalence classes. And what this simple computation tells you is that determinant is of a matrix it does not change if I go from one matrix to another, as long as I stay in the same equivalence class. Okay, I mean, all this is easy. That similarity is an equivalence relation is easy. That determinant is constant on equivalence classes is easy. But it's good to keep these easy facts are good to keep in mind, because they form part of the picture of the determinant that you should have. So the determinant is a function from the space of n cross n matrices to the real numbers. The real numbers are partitioned into equivalence classes by the equivalence relation given by similarity. And the determinant function is actually constant on the equivalence classes. So its value on a matrix depends only on the equivalence class of that matrix, on the similarity equivalence class of that matrix. Okay, so this was all preparation. So let us come back to, so our main aim is to define a function. So let V be a vector space, always real, because that's all we are dealing with, but that is almost irrelevant. Dim V is n. So whenever I write is n, I mean n is an actual integer, non-negative, positive integer. So in particular, it is V is a finite dimensional vector space. So earlier we were dealing with dit was a so dit. So our matrix, our determinant so far dit n was a function from this of this kind. So we are moving on from here. Okay. So now let me. So dit will be a function from somewhere to somewhere. What should come here? Well, I've already told you what comes here from the space of linear maps from V to V. Now there are several notations that you can have for this. I prefer this. Okay, this is the notation I have used in the notes. So LVV is the set of linear maps V to V. Now note that this is more than a set. It is a vector space. This is actually a vector space. Since given two linear maps A hat and B hat, you can add them up. So the action on a vector V is by definition A hat V plus B hat V. But in fact, because these are linear maps from a vector space to itself, you can even compose them. So given A hat and B hat, you can compose them A hat B, A hat B hat, where A hat composed with B hat is a linear map whose value on B is by the definition of composition, this. You first apply B hat to V, and then you apply A hat to that. So this is a vector space in which you can actually multiply the elements, and there is associativity, there's bilinearity, etc. There are lots of properties that these two operations satisfy between them. Okay, for example, many properties, just like matrices. In fact, this is just an avatar of matrices. Many properties, among them A hat, B hat plus B hat prime is A hat composed with B hat plus A hat composed with B hat prime, etc. Okay. So now, where are we? We are going to now define dit from LBB to R. And just as when we defined the determinant of matrices, for a little while we had a subscript. So let me just put a subscript. This is not usual. This is not standard. Putting the subscript, not a standard notation. The subscript. So soon we will drop it. Okay, so we will define it in a moment, but the important thing is you should remember that dit V of AB, A composed with B, A hat composed with B hat, is dit A hat into dit B hat. So here it's composition, and here it's multiplication of real numbers. Why? Yeah, dit V. Okay. Then dit V A hat is non-zero if A hat is an isomorphism. That's i.e. invertible. So for a matrix, invertible means there is an inverse matrix. For a linear map, invertible means the same thing. There is an inverse linear map. Okay, which is also the same as saying it's 1, 1 and onto. And dit V of the identity map is 1. And now that we have defined similarity of matrices, you can define similarity of linear maps in exactly the same way. Say that A hat and B hat are similar if there is an invertible linear map T hat such that B hat is T hat A hat T hat inverse. And again, from all that, it is clear that this is an equivalence relation on LBV, and dit V is constant on equivalence classes. Okay, so how are we going to define, dit V?
Sir, could you please go a little slow? Like there's so much of material coming at a high rate.
Very good. Yeah. Sure. Yeah. So so I can go. I can go slower, and if you wish, I can even repeat any part that. Why don't I just quietly, slowly scroll up, and then you stop me. So that will give you some time to look at it. Today, for a change, I think I have written somewhat clearly. So it will give you some time to look at what I have written. And then you stop me wherever you want me to explain. Okay, so I'm just going to go slowly up.
Excuse me, sir.
Yeah.
So can you please explain a bit about the determinant of linear maps, because I had some network issues, so I couldn't.
No, I have not yet defined it, by the way. So
okay,
I'm going to define it. Okay, so let me just run through again. So my exposition, I start by recalling that we have defined for these various determinant functions from the space of n by n matrices to R. And if you fix n, you can just think of it one function for the moment. Okay, and so this is the many properties, but the most important is that it's multiplicative. That if you take the product of two matrices, the determinants multiply. The determinant of a matrix is non-zero if and only if the matrix is invertible, and the determinant of the identity matrix is 1. Okay. So now we are going to go on to define the determinant of a linear map from a vector space to itself, provided the vector space has finite dimensions. And while we are going to do that, just remind you that what we have done is already a special case, because n by n matrices can be thought of as a space of linear maps from column vectors of length n to column vectors of length n. So we have already done a special case of what we want to do. This is what we want to do. And what we have already done is a special case of this, because this is a space of linear maps from column vectors to column vectors. Every linear map from column vectors to column vectors is given by a n by n matrix, and that matrix is unique. So this is, so now as a preparation for what we want to do, I want to again sort of say one more thing about determinants and something about matrices also. You say that two matrices are of the same size, n by n, square matrices of the same size are similar if one can be got by from the other by conjugating with an invertible matrix. So this is called conjugation. This operation, you take a, pick an invertible matrix and do this thing. This new matrix is got from A by conjugating with an invertible T. So that is a phrase that you should get used to. Okay. So conjugation by an invertible matrix. So if you say that two matrices are similar, if they are conjugate, if one can be got from the other by conjugating by some invertible matrix, then this is an equivalence relation on the space of n by n matrices. Because if A is so call this similarity, then if every matrix A is similar to itself, because you can take T to be the identity matrix. If A is similar to B, B is similar to A, because if A, so A is similar to B, if this is true, and then if this is the case, then A is T inverse B T. Copy done? Excuse me. Yeah, just give me a minute, please. So, and if A is similar to B and B is similar to C, then A is similar to C. So this is an equivalence relation. So whenever I have an equivalence relation on a set, the set gets partitioned into equivalence classes. This is something I suppose you know. Partition means the set is a union of subsets, and they are disjoint, mutually disjoint. So because the determinant is invariant under similarity, it's actually a constant function on each of these equivalence classes. So this is just context. I mean, you know, this helps you think. See that you have encountered this strange beast called determinant. So you have to get familiar with it. You have to learn to understand what are its properties. So this is how you proceed, right? So now I move from n by n matrices to linear maps from a vector space to itself. And this is a notation that we have used for that set. If V is a vector space, this curly L, V comma V, is my notation for the set of linear maps from V to V. And this is actually not just a set. It is a vector space in its own right. And in fact, it's a vector space of dimension n squared. You can add linear maps. You can even multiply them. Multiplication is just composition. And it, you know, these operations have very nice properties. Now, we want to define some notion of a determinant from here to here. And I temporarily give this notation dit subscript v. Soon we will drop that v. Okay, just as we drop the n, we will drop the v. And I have not yet defined this object, this function dit v, but it will have exactly the same properties that our old friend dit had. Namely, if I take two linear maps from v to v and compose them, the corresponding determinants multiply. This is non-zero if and only if the linear map is invertible. A linear map from a vector space to itself is invertible if there is another linear map whose such that the composition is the identity. And a necessary condition for this and sufficient condition is that the linear map should be 1, 1 and on 2. Okay? So in fact, we use these things interchangeably. And the determinant of the identity linear map is 1. And further, just as we define similarity equivalence relation on n by n matrices, you can define similarity equivalence relation on linear maps from a vector space to itself. And again, this is an equivalence relation, and the determinant that we are going to define is going to be constant on these equivalence classes, because for the same reason, for the same easy proof. Okay, Shakti, is that okay? Can I now go on?
Yes, sir.
Yeah, very good. So now how to define dit v? In fact, we saw a glimpse of that in the last class. As somebody said, and I have also said, the difference between a vector space of dimension n and Rn is just that you have to choose a basis. Once you choose a basis, then there is no difference between a vector space of dimension v and column vectors of length n. So this is how you do it. So I'm going to do this in, first of all, in sort of abstract. So first abstract picture. Start with the linear map v to v, a hat. Start with choose the basis E1 and for V, define A to be the matrix representing A with respect to this basis. I.e. A equal to Aij and A hat E I is sigma E Ji Ej. Remember, there is this little thing that the subscript that you yeah, we've encountered this. So define dit A dit B A hat to be dit N A. Check that if E1 prime En prime is another basis, then A hat prime and A. Be very careful, no hats. A prime and A are similar matrices. So dit and A prime is equal to dit A. So dit B A hat is equal to dit A is equal to dit A prime, independent of the choice basis. So this is not the abstract picture. This is actually, I will not give too much of this. I'm just going to leave it like this, because I think explaining this doesn't help. This is something that you just have to check for yourself, read the notes. Okay. So that's it. And then you can just go back and check that dit V that we define like this has all the properties that I claimed. It's as simple as that. So I want to define the determinant of a linear map from V to V. Choose any basis, look at the corresponding matrix, and define the determinant of the linear map A hat to be the determinant of the corresponding matrix A. The point is, if I choose a different basis, I get a different n by n matrix. But you can check that the two matrices that I get for two different choices of bases are actually similar n by n matrices. That means there is an invertible T that takes one to the other under conjugation. Therefore, determinant of A is equal to determinant of A prime. So I can just define determinant of A hat to be determinant of A for any choice of basis. And once you do that, everything else follows. So this is something that you just need to check that, whatever I claimed is actually true. It's all written out in the notes, and it's not difficult to check. If you provided you keep track of your indices and your summation and what is happening. And what is this invertible matrix T that will give you the equivalence? So then you have to ask yourself, okay, there is a T that will take you from A to A prime. What is the T? That T has to do with the two different choices of bases that you have made. Given two choices of bases, there is a invertible T, n by n matrix T that gives this change of basis, and that is precisely the T that intervenes to give the similarity of A and A prime. So this is something that you really must write out and check and get all your indices and your summation correct. It is not going to be any use if I do it in class. Yeah, so I don't think I want to spend more time. So what do you think will help here? So maybe I should do an example. Shall we do an example? Maybe we should do an example. Okay, let's do an example. I have not prepared this example, so I might get into trouble. Okay, let P2 be the space of polynomial functions R to R of degree less than or equal to 2. So P of X, so P in P2, if and only if P of X is A0 plus A1X plus A2X squared, where A0, A1, A2 are real numbers. Consider the linear map P2 to P2, P going to P prime, the derivative. So let's give this a name. So this is A hat, okay? So in other words, A hat acting on a polynomial is just the derivative of the polynomial. So what is dit of A hat? Okay, so there is a, if you've been listening carefully and understood what I have said, there is a computation-free way of saying what determinant of A hat is. So just don't, if you see the answer, please don't say it, let everybody think. So in other words, before I defined the determinant of a linear map, I made some claims about the determinant. Then I defined the determinant, but I did not verify that the claims are indeed true. But that is also difficult, not difficult. All these things you have to go back and check. But at the moment, I'm asking you to recall everything that I said today about the determinant of a linear map from a vector space to itself. And somewhere within there is a clue to my question, which is actually quite easy if you notice one fact about this particular A hat. So I think some of you would have seen exactly. Yeah. So at least one person has seen the point, but I want to give everybody time to think about this. So let me just scroll down, and where I stated, yeah. So I stated the various properties of the determinant of a linear map. And if you stare at this and then stare at what our particular A hat is, which is the derivative, take a polynomial of degree less than or equal to 2, and the linear map A hat acting on this polynomial is just taking the derivative of this polynomial. Anybody else? So far I have one person. Okay, 2 people have it. Just give me a direct message. So 3 people. Yeah. So people are chiming in. I want to give everybody time to think about this. Yeah. So far I have some 12 people chiming in, 12 or more. Very good, excellent. So yeah, so those who haven't yet voted, please vote. Meaning, just send me a direct message. At least a guess, and if possible, short reasoning, what the answer should be. Just stare at the page that is in front of you. And also think of the particular A hat. Yeah. Not everybody, there are still people who are sitting on the fence, who still not voted. So let me just go down and yeah. Srimati, do you have opinion on this?
I sent it, sir. I think. Oh, can I say it?
No. So you can type it.
No, I typed it essentially.
You did already. Very good. How about Siddhant?
Sir, I'm not sure. Like, I didn't understand the question properly enough. I think I'm not.
So, okay. So what is it that, oh, very good. That's excellent. So see, that's the kind of thing I really want feedback of that kind. Do you understand what this curly P2 is? It's something that you encountered before. You've encountered this in PD, polynomials of degree less than or equal to D.
Yes.
So polynomials of length degree less than or equal to 2. Polynomials either quadratic, linear, or constant. Okay. So that is a vector space.
Yes.
Right. And you can look at the linear map from this vector space to itself. Just take a polynomial and take its derivative. Okay. Since the derivative of a polynomial cannot have higher degree than the polynomial you start with. So this is a linear map from polynomials of degree less than or equal to 2 to polynomials of degree less than or equal to 2. It's a linear map from this vector space to itself.
Yes, sir.
What is the dimension of this vector space? In fact, this is also a problem that you have seen before. So it is a finite dimensional vector space. In fact, the dimension is 3 because a polynomial, okay, because there are 3 coefficients A0, A1, A2. The polynomial is determined by these coefficients. And this, if we add 2 polynomials, these coefficients add. So this is, okay. So this actually gives you an isomorphism of P2 with R3, associating to each polynomial the coefficients A0, A1, A2, gives you an isomorphism of P2 with R3. So it's, and now you have a linear map from V to V, namely take a polynomial and take its derivative. So, okay, so you have to compute the derivative. And the point is, okay, now I am going to give the answer because if I take the derivative, this is not an injective map because if I take any constant polynomial, its derivative is 0. So it's not injective. So it is not invertible. Therefore, the determinant must be 0. So without any computations, if you believe the properties of dit V that we have, we have just listed, it is the determinant is 0. And okay, so let me now, okay. So note A hat is not injective since A hat of the constant polynomial is 0 for all A0. Okay, constant polynomial, any constant polynomial. Because if I take the derivative of the constant polynomial, it's 0. Therefore, A hat is not injective, implies A hat is not invertible, implies dit of A hat is 0 because it's one of the properties of the dit V that everywhere I should put a V that if I have dit V of a linear map is non-zero if and only if it is invertible. That was one of the properties that I had listed here. Okay, so now let us actually compute the DIT by our recipe. Our recipe for computing the DIT of a linear map is choose any basis, look at the corresponding matrix of a linear map, and take the determinant of that matrix. Okay, so what is the basis that we will choose? Choose a basis. Choose a basis for P2, and the basis, well, let us choose the following basis. So E1 is the constant polynomial 1. E2 is the polynomial x. E3 is the polynomial x squared. Okay. Now, a hat of E1 is 0. A hat of E2 is 1, which is E1. A hat of E3 is 2x, which is twice E2. Siddhant, do you understand what these computations?
Yes, sir.
Yeah. So I am. So does everybody understand these computations? Because this is important. So I have taken this vector space of polynomials, chosen a basis for that vector space, namely the first basis vector consists of the constant polynomial 1. Remember, polynomials are, these are specific functions from real numbers to real numbers. So when I say 1, it is the constant function 1. That is what this means. This means this is the function x. This is the function whose value at every point is x. X is x itself. This is a polynomial x. E2 is a polynomial x squared. Siddhant, are you okay so far?
Yes, sir.
Yeah. So now I take my linear map A hat acting on each of these basis vectors. So what is A hat acting on E1? Take the polynomial corresponding to the basis vector E1 and take its derivative. What is the polynomial corresponding to the basis vector E1? It's a constant polynomial 1. Its derivative is 0. Okay, so I get 0. A hat acting on, by the way, so this 0 is a 0 in the vector space P2. When I say A hat of the constant polynomial is 0, I mean it's a 0 function. Okay. A hat of E2 is the derivative of the polynomial x, which is the constant function 1. So which is E1. So that gives this. A hat of E3, which is the polynomial x squared, is the polynomial 2x. That is 2 times this basis vector. So I have 2E2. Siddhant, are you okay with this?
Yes.
Yeah. So now, what is the corresponding matrix? A is, I better be careful with this, but I'm not going to be careful. It's in fact, this is where it's important whether you are summing over the first index or the second index, but I'm going to be careless with that because I don't have time to be careful. And it doesn't matter in this case because if I make the wrong choice, my matrix will be the transpose of the matrix that I should be taking, and the determinant will not change. So I'm going to be careless. So anyway, a hat of E1 is 0. So that means the first column is 0, 0, 0. A hat of E2 is 1. So that gives me 1, 0, 0. And then I'll have 2, 0, 0. So this is A. And now if you compute its dit, well, you can do a computation expansion by minors of the first column. It's 0 times something plus 0 times, so 0 times something plus 0 minus 0 times something plus 0 times something. So this is dit of A is 0, which proves that dit of V A hat is 0. Okay, so now let us take another linear map from P2 to P2. Example prime. Let me call this now, I shouldn't call it example prime because prime is already derivative. Example 2. So let me call this example 1.
So we define A cap V to be the matrix A times the corresponding vector, the matrix V. But how will we multiply the matrix like A with the basis vector E1, E2, E3?
I didn't understand your question.
Like how will like
No, wait. So ask with respect to what I have written. Is there something that you don't understand here?
Yes, A cap E1 will be written as like A times E1.
No. What is my definition of A hat?
No, like previously we defined the.
What is my definition of A hat? What is, see, I start with the definition of A hat, and then you have to find the corresponding matrix by choosing a basis vector, a basis. What is my definition of A hat?
Like it gives the derivative of the particular polynomial.
Yeah, so A hat is the derivative. So A hat comes first. The matrix comes later.
So how do we define the matrix here, like for this particular?
Well, so that was what I was doing here. No, how do you go from a linear map to a matrix? So that is here. The matrix A is defined by this. These are the entries of the matrix. The entries are defined by this equation. This has been explained in the notes, but that is no. But that is okay. So I'm prepared to spend time here. Shakti, what is your confusion?
So I will have to think upon that. Like
no. Let us. I think this is actually the basic point. You start with a linear map from a vector space to itself. See, the point is linear maps need not be defined using matrices. And in fact, this is an example. I have a vector space and I defined a map from itself, vector space to itself. There was no matrix in my definition, right? Take a polynomial, take its derivative. Now, to have a matrix, you have to choose a basis. And there are many choices of basis. So I've choose one basis here. The basis consists of three polynomial functions. One is the constant polynomial function 1. The second is the polynomial function x itself. The third is the polynomial function x squared. So do you understand the choice of basis?
Yes, sir.
Yeah. Now, once I have chosen a basis for a vector space, and now if I am given a linear map, then I can associate a matrix to that linear map like I have done here. So how to define the matrix, what do I have to do? I have to give each of its entries, right? What are the aij's? This is the question to define A. Now, apply A hat to one basis vector after the other. So take the first basis vector, apply A hat to that. Whatever I get can be written in terms of all the basis vectors with some coefficients aji. Take all these guys. How many of these guys are there? And there will be n squared coefficients, because for the first basis vector, there will be n coefficients. For the second basis vector, there will be n coefficients. As I go from the first to the last basis vector, I will get n squared real numbers. Put them all together and package them into this matrix A. So this is how I associate a matrix to a linear map. Then take the determinant of this matrix. That gives you a real number associated to the linear map. Now, because if I choose another basis, the two matrices are similar, the determinant does not depend on the choice of basis. So I define the determinant of a linear map. That's the philosophy. Okay. Now I apply this philosophy to this example. So now again, so you said you have to think. So think about this. I mean, and let me not hurry forward until you are happy.
Yes, sir. I got it. Yes, sir. Thank you, sir.
Yeah.
Sir, I think Shakti's original doubt was that since you defined a matrix here, when we initially did matrices for the space of column vectors, we were writing A hat of V, like the map, the A hat applied to V.
No, but that is the point. So when I have a matrix, n by n matrix, then the corresponding A, so when I think of it as a corresponding linear map, then it becomes A hat.
Yes, sir. Sir, no. I think he was just asking for a correspondence between the two ideas, that if we wanted to write the image of V as a, for example, if you wanted to write the image of E1 vector in the matrix product form, so A times something, then how would we do that? So I think in that case, you would just correspond between 1 and 1, 0, 0. Similarly, X would go to 0, 1, 0, 1. So I think that's what Shakti was asking.
Yeah. This is something that, it is there in the notes, how to go back and forth between this. You have to just do this in various ways, and so that you become familiar. Okay. Anyway, so the matrix corresponding to A hat is this A, and its determinant, which you can check, is 0. Now let's look at another example. Let me now call it B. B hat of P is P plus P prime. Okay. Now, if you look at the corresponding linear map B, matrix B, it will turn out to be 1, 1, 0, 0, 1, 2, 0, 0, 1. And the determinant of this, you'll find out, is 1, which implies the determinant B of B hat is 1. So I have not, I mean, this is just a claim. This is something you have to check. Okay, I will put this up here and I will take a break, and you guys, you can even discuss among yourselves And after we come back, I will catch up with the discussion. Yeah, I'm back. So do you see this? You first of all see that B has to be of this form. Hello? So first of all, the first question is, why is B of this form? Because then it's clear, because once somebody tells you that you have a 3x3 matrix like this, to see that its determinant is 1 is very easy, okay? So why is B of this form? So here is a hint. So why is B of this form? and somebody says he doesn't understand, hint, the linear map B hat is our earlier friend A hat plus the identity linear map B to B. Because what is B? So, because since IV plus A hat, by the way, V is P2. Huh? Since IP2 plus A hat acting on any polynomial P is by definition IP2P plus A hat P, but IP2P is P and A hat P is P prime. So here is a hint. So the new linear map that we are talking about is the sum of the old linear map A hat, which took a polynomial and derived it, and the identity map, which takes a polynomial and gives you the same polynomial back. So it's a sum of these two linear maps. So that is a hint. There was somebody who said that he doesn't understand why B is of this form. Now, do you now see why B is of this form? Okay, so okay, so we are now coming up to the end of our class. I'm just going to leave you here. Just think about this and go back and just, this is something that you really need to do with pencil and paper and sweating the indices. There is no amount of my lecturing that will tell you how to go from linear maps to matrices and back. Yeah. But you really need to do that. You really need to do the, it's like, sometimes you just need to go to the gym and work out. So that thing you need to do. This is not difficult, but you just need to understand how to go from matrices to linear maps and back. And I think for some of you at least, the problem is that matrices from quite a bit, and then you have to really, and the point is matrices get you used to a certain way of thinking, which is very efficient if you are computing with matrices. But if you want to work with abstract vector spaces and linear maps, just given directly in terms of the vector space, and without a basis, without a matrix in it, then you need to get used to how to translate from the abstract definition of the linear map to a matrix definition of the linear map and back. So I'm going to stop now. Let me just stop for a start.